All right, so today I want to continue with the discussion of DMRG in terms of matrix plus states. I also talk about time-dependent DMRG, and then give you some physical examples that we haven't discussed. Yesterday I left here. Why does the DMRG work? So we know that the DMRG basically compresses the wave function, the ground state wave function, and it does it in a very efficient way, but we don't quite understand why it works. And it all comes to the behavior of the singular values, right? We do a singular value decomposition, and the singular values basically tell us what states to keep, what states to throw away. And the behavior of these singular values is going to tell us how much information we are actually losing along the way. So here I'm showing two examples. For instance, imagine that the system behaves as the blue curve here. This is the number of eigenstates that we keep, and this is the value. And we see that if we truncate somewhere here, we lose very little weight. But if the curve behaves as the red one here, then this is bad, because basically our approximation is very poor, and basically we're getting pixelation in our image, and we're losing a lot of information. So the question is, why in some cases the systems behave as the blue curve, and why in some cases it does it as a red curve? And in order to understand this, we need to change the discussion to the behavior of the entanglement. And we heard a lot about entanglement, of course. So this is, we know what entanglement is. But sometimes, in practical terms, it's not so obvious. Because imagine you have a wave function that looks like this. You have two spins, and your wave function is, this is very similar to the example that Andrian, the maestro, gave, basically in terms of bosons. So imagine you have two spins, and you have a superposition that looks like up-down, plus down-up, plus up-up, plus down-down. And at first sight, you may think that this is a highly entangled state. But if you look at this more carefully, you realize that this is basically a product of two states. The first qubit, let's say, or the first spin in the up plus down state, and the second qubit in the up plus down state, which is basically the state pointing along the x direction, and up in the direction up along x, and direction down along x. So this is actually a product state. So, but just looking at this state more carefully, you realize that entanglement is, in order to determine if a wave function is entangled or not, we need to come up with some sort of algorithm. So, on the other hand, if you have a state like this, which is a triplet between the two spins, you cannot separate into a product state. So this is actually a maximally entangled state. And in order to determine whether a state is maximally entangled or a product state, we need to first talk a little more about the Schmidt decomposition. So I told you that we have a wave function that is broken into left and right parts, or system and environment. And it's described in terms of these coefficients that now form a matrix, psi ij. So when we do the Schmidt decomposition, and we write the wave function in terms of the eigenvectors of the reduced density matrix, these coefficients, lambda, are our Schmidt coefficients. And the number of coefficients that we need to keep, or the non-zero, the number of non-zero coefficients, is basically what's called the Schmidt rank of the state. So if the Schmidt rank of the state is 1, then we only keep a single state here, and it becomes a product state. So that's an easy way to see that it's a product state. And this automatically gives us the basis in which this wave function becomes a product state. On the other hand, if all the coefficients are equal, and basically proportional to 1 over the dimensions of Hilbert space, then this is basically proportional to the identity matrix, and the state is maximally entangled. So how does the so this in some way the number of states that let's look at this decomposition again. So when we keep a few of these lambdas, basically what we are doing is we are transferring entanglement from the original representation into the new representation. And now the entanglement is sort of concentrated or accumulated into a few states, right? That's what's happening, basically. So imagine, for instance, I don't have a slide about this, but imagine you have by the way, if you have a spin chain, and you look at the reduced density matrix of the first site on the left end of the chain, the density matrix is going to be a 2x2 matrix, right? So the Schmidt decomposition is going to have rank 2. So you can see that even though your environment is huge, it may have 100 spins, the density matrix still has rank 2. So all the entanglement between the single site and the chain is contained in only 2 states. And it cannot be in more states because you only have up and down for the site. And we know that the density matrix is the same for the left and the right blocks. It has the same eigenvectors, right? And the same eigenvalues. So so the efficiency of the DMRG then is determined by the spectrum of the density matrix or by the Schmidt coefficients. And this is nothing else but the entanglement spectrum that we've heard a lot about. And if these coefficients decay very fast, for instance, exponentially, then this is good for DMRG. If they decay very slow, this is bad. So now we have to figure out why in some cases they decay fast and why in some cases they decay slow. And to do that, we need to quantify entanglement, and we know how to do that, right? We use the von Neumann entanglement entropy. And the von Neumann entanglement entropy is nothing else but, in this representation, the sum over the eigenvalues of the reduced density matrix, lambda square log lambda square, right? And or in terms of the density matrix, of course, it's the trace of rho log rho. So for this, I told you that this state is a maximally entangled state, right? And this is obvious now if we look at the reduced density matrix of the left spin, which is proportional to the identity. It's 1/2, 1/2. And the entanglement entropy is log 2. So now we can generalize this and see the following. If the entanglement is a periodic, if the state is a periodic state, we only have one Schmidt coefficient surviving, and all the rest are 0. And the entanglement entropy is 0. So basically, entanglement entropy tells us, 0 entanglement entropy basically tells us that it's a periodic state. And if it's maximally entangled, they're all proportional to 1 over the dimension, and the entanglement is log d, log of the dimension of the Hilbert space. So it turns out we heard also that entanglement obeys an area law. In 2 dimensions, the area law can be pictured as follows. I mean, this is a very very artificial example, but it gives us some intuition. So imagine like you have a state that is a dimer covering on the square lattice, like this. And now you draw some boundary, and you want to look at the entanglement between the inside and the outside of this region. And all you have to do, because this state is basically product of singlets, and the entanglement is going to be the sum of the entanglement of the bonds that my line is cutting through. So we know that the entanglement entropy for single singlet is log 2. So here we have the number of bonds that I cut times log 2. And the number of bonds that I cut is proportional to the length of this boundary. And this tells us that basically the entanglement entropy is going to be basically proportional to log 2 times the L, the area, or the perimeter in this case, right? So in 2 dimensions, the area becomes the perimeter. In 1 dimension, the area becomes a single point. And that's why DMRG works so well, because entanglement, well, we have to be careful when we talk about one dimension. So I'm going to get to that next. So it turns out that in one dimension, we can have gapless systems or gapped systems. And the behavior is going to depend on each case. We know that the entanglement entropy using conformal field theory, this is a critical system in one dimension. And we know that conformal field theory tells us that the entanglement entropy basically, this is not always the case. We can have critical systems in 1D that are not conformal invariant. But this is a typical case of a conformal invariant one-dimensional chain. And you see that, conformal field theory tells us that the entanglement entropy goes as C/3, where C is the central charge, times log of the length of the boundary. So clearly, this is not quite an area law, but it's also not a volume law. It goes as a log. And with periodic boundary conditions, it goes, with open boundary conditions, it goes as C/6, so it's half. So this is going to be important. So here you see basically the entropy as a function of system size or block length, and you can fit it nicely to this expression. This is in a log scale. And you see that basically there's a factor 2 between one and the other. And this factor 2, as I said, is going to be important. You remember that for periodic boundary conditions, DMRG didn't work that well. And that's going to come back to us. So basically, this is how the entropy, and the entanglement entropy, determines the efficiency of DMRG. So it turns out that the number of states that we need to keep is proportional to e to the s, where s is the entanglement entropy. So for a gap system in one dimension, that means that at some point the entanglement entropy saturates beyond the correlation length. So if your system length is larger than your block length is larger than the correlation length, the entanglement entropy saturates, and the number of states that you need to keep is constant. For a critical system in one dimension, it becomes proportional to L to some power. For gap systems in 2 dimensions, again, it goes as the exponential of L, where L now is going to be the length of the cut, the boundary between the left block and the right block, right? So imagine a cylinder in 2 dimensions. We cut it in half. So this L now is the length of the circumference. And in general, in 2 dimensions, most systems obey the area law, except for free fermions. And it turns out that for periodic boundary conditions, the area is twice, right? Because we have 2 cuts. We have a cut in the middle, and we have a cut at the origin, because we have to close the boundaries. And because of that, instead of going as m, it goes as m squared, the number of states that we need to keep. So if in one dimension we need to use 100 states for a Heisenberg chain with open boundary conditions, with periodic boundary conditions, we need to use 10,000, right? So that's why it's so, periodic boundary conditions are such a pain. All right, so this is the connection between DMRG and or matrix states and entanglement. And this is how we know when DMRG will work and when it won't. This is also telling us why it doesn't work so well with long-range interactions. With long-range interactions, your boundary is basically huge. It's like a volume, really. And that's why we need to keep more states. So now I'm switching gears because I want to go into matrix states. So to do that, I want to establish a connection, and I want to talk a little more about how you transform the wave function when you plug in when you add 2 sites. And this is just a technicality, but if you look at the notes more carefully later, you're going to make the connection. So, and this is something that we need also in time-dependent DMRG. When we when we add a site to a block, we use a unitary transformation, right? We change the basis. But we can also rotate the wave function. Right? So it's just a unitary transformation on the wave function. So the thing is that we need to apply two unitaries. We need to apply a unitary to the left and a unitary to the right. And this is what I just wrote here. So basically, if you write your basis in terms of the left block, the spin, and the right block, you need to group these two, transform them to the new basis, these two, transform them to the new basis, and you get the new wave function after the rotation. And this is important because when we do time evolution, we need to propagate the wave function in time. We need to transform the wave function as we do sweeps. So this transformation is just a change of basis, and it's basically given in terms of this. I'm going to call this matrix U, which is basically the matrix of eigenvectors of the reduced density matrix. And now I'm going to do a change of notation. I'm going to call this matrix A. And I'm going to write the indices in a different way. The index corresponding to the single spin that I added to the block, now it's going to be like an external label here. And this is going to be a matrix now that depends only on the alpha L and the alpha L minus 1 before I added the new spin. So you see that basically this is now a matrix. This is two matrices, one for the spin up, one for the spin down. And it's just the transformation matrix written in a different way. So when I do this rotation, I go from alpha L minus 1, I add the spin to alpha L. I'm basically multiplying by A, right? This is just the same written in terms of A. I can do the same for alpha L minus 1 and write another A for alpha L minus 1 and alpha L minus 2. So I can do this recursion all the way, and I end up with the product of A's, of matrices A's here. As you can see, and here at the end, I end up just with single spins. So this is basically a wave function in the basis of the original basis of single spins. So because basically what I'm doing is I'm undoing or retracing back all the changes of basis that I did during the DMRG. And you end up with this expression where each coefficient is basically a contraction of matrices. You see that basically I'm contracting this index alpha 1 with this alpha 1, this alpha 2 with alpha 2, and so on and so forth. So this contraction gives you scalar, just a number, and that's the coefficient in the wave function. One observation is that if you have open boundary conditions, you end up here at the end with the vector. So you have only one index, not two. So these are all two-dimensional matrices, except for the last one, which is a vector. And this is what's called a matrix product state. And this is a matrix product state representation of the DMRG block. Let's say this case is for the left block. So what people realized early on, like Ostrlund and Romer, that you could write this wave function in this form, but only in 2000 or so, people understood that you can use this as a variational expression and just optimize the wave function by optimizing these matrices. And basically, that's what DMRG is doing in the end. It's the same thing. So let's see that. So these 8 matrices, I remind you, they are nothing else but the rotation matrices U that take you from one basis to another. So they are orthonormal. And you have to be careful because this is not the case for any matrix product state. This is the case for the DMRG matrix product state because it comes from all these block transformations. But in general, a matrix product state, for instance, that you can write any matrix product state and it doesn't have to be normalized necessarily. And normalization is a big issue actually in DMRG because if you have an arbitrary matrix product state and you want to normalize it, it's a really computationally hard problem. And that's the problem with periodic boundary conditions, actually. Graphically, these matrices look like this. The first one is just 1 by 2. It's a vector. The second one is 2 by 4, because you go from two states to 4 when you add another spin. So every time you add a new spin, you multiply times 2. Right? The first one is 2 times 4. The second one 4 times 8, and so on and so forth. At some point, you cut the dimension of your matrix. You keep it constant because you're truncating. And it becomes of some arbitrary size. And at some point, you reach the other end, and they start shrinking again. All right, so again, you can do the same for the right block. For the right block, you just add sides to the right block, and you do a similar transformation, and you get B matrices. And these B matrices are different than the A matrices on the left. So these are two different, what's called canonical representations. We have the left canonical representation for the left block and the right canonical representation for the right block. And they are both normalized. And at any given point, the DMRG wave function is going to be basically your left block, which is written in terms of A's, your right block, which is written in terms of B's, and there is some coefficient connecting these two. And if you just group this coefficient with this A to the left or with this B to the right, you can basically write it down as this, a product of M matrices. And these matrices could be A's or B's. So this is the general form of an arbitrary matrix product state. The nice thing about these matrix product states is that they are amenable to a nice graphical diagrammatic representation, which is as follows. You've probably seen this before. Many of you know what I'm talking about. Maybe you have not. So this matrix S has 3 indices. One is this external label, that is the physical index that corresponds to the site degree of freedom, which is a spin that could be up or down, or could be a fermion. It could be empty, occupied, double occupied, or up or down. So you may have four states, or boson, which you can go from 0 to infinity in that case, because you can have an arbitrary large number of bosons on one site. And that's what makes bosons a challenge. And then this is a matrix with indices alpha and beta. And this is what I write on the horizontal line. So this left index alpha and this right index alpha are called bond indices. It basically correspond to the new basis. When you go from beta, the beta basis, you add the spin S, you get the alpha basis. You remember this is a transformation. And a vector, it has only one index alpha and is written just like this, or with the arrow to the other side, either way. And a contraction between two of these is written like this. Just contract the alpha. So let's say we have 2 of these A matrices. So we're going to have A matrix on the left and A matrix on the right, and you're contracting the index here, and you connect it like this. And this implicitly is telling you that you're summing over alpha 2. So this is going to give you a new matrix that's going to have 2 physical indices and 2 bond indices, alpha 1 and alpha 3, because the alpha 2 is implicitly summed over. Feel free to interrupt anytime. I know this is a lot to digest, but you can look at the notes carefully or the reviews, the literature that I gave you. So the thing is that for open boundary conditions, as I told you, the last 2 matrices are vectors, and your matrix product state, the coefficients are represented like these. If you have periodic boundary conditions, you have to also trace over these indices. So you're going to have another matrix on the left and the right, and you have to trace over contract those 2 matrices too. So you see now what the problem is with DMRG with open boundary conditions. With open boundary conditions, you use this wave function. with this form. Implicitly, DMRG is optimizing this variational wave function, right? And it's taking a vector at the two ends. Now you go to periodic boundary conditions, and you realize you don't have to use vectors, you have to use matrices. But DMRG is still using vectors. So that's why, that's the second problem with periodic boundary conditions. Then. As I told you earlier, one problem is that you need to keep more states because of the area law. The second problem is that you're using this variational wave function for periodic boundary conditions while you should be using this one. All right? So DMRG cannot deal actually with this form of wave functions. If you want to do periodic boundary conditions using this kind of wave functions, you need to use a modified version of MatrixState optimization. So MatrixState states have some interesting properties. I'm not going to go over them right now. You can add MatrixState states, but when you add two MatrixState states, the size of your matrices double. You can gauge transform them, if you will. So actually, you can apply a unitary transformation. Imagine you have this contraction. You can introduce two unitaries here, basically a resolution of the identity like this, and then move this x to the left and this x inverse to the right, and get two new matrices. Then you can write operators also in this representation. Graphically, an operator would look like this. An operator acts on the physical index. So it takes, for instance, S plus, S minus, they flip the spin. So we take a matrix A up to A down. That's what basically it does. And this is how it acts. Basically, if the alpha and beta indices are not touched, you only act on the physical index, either inverting it or something else. If you have a unitary, for instance, like when you do time evolution, we're going to see you need to do Suzuki-Trotter decomposition of the state. And the Suzuki-Trotter decomposition allows you to apply the exponentials in pairs of sites. And then you are basically transforming, applying an operator on two sides at the same time. But another way to see this, it doesn't have to be a unitary. You can apply S plus S minus on two sides, for instance. Imagine I'm taking S plus S minus. And this operator is basically now a product of two operators, S plus S minus, acts on two physical spins. And basically, the new state is transformed like this. You know, the alpha 4 and alpha 6 are not touched. This is implicitly added over, so it only acts on the physical indices again. And this is done, given by the coefficients of u, right? So u goes from the original values of S4, S5 to new values of S4, S5. So the matrix basis, you know, I told you about the left canonical, the right canonical, and the left canonical looks like this. Now, in this graphical representation, it looks as a contraction of matrices where you have this right index open. And for the B's, you have this left index open while you're contracting over all these matrices. And it turns out that, well, if you take this one, you want to calculate an overlap with another state, left canonical state, with different S's, or with different alpha L. What you have to do is contract the physical indices like this. So this is how you calculate an overlap. And it turns out that because it's orthogonal, you know, this basis is orthogonal, you're going to get the delta. This is going to be a delta of alpha L prime. And you can do the same with the betas. So again, long story short, the wave function in diagrams would look like, remember I told you, you have all the left block in terms of A's, the right block in terms of B's. You have something here in between connecting them, and graphically it looks like this. So you're going to have your left canonical representation for the left block, your right canonical representation for the right block, and this coefficient, which is basically a matrix without any physical index connecting the two. And what you do, basically, when you do DMRG, is you move left and right with this psi here, and you try to optimize. Now, you see that here, the psi involves, connects only two sides in the middle. So this is kind of equivalent to a single-side DMRG. You know, I told you in DMRG you put two sides in the middle. If you do matrix state optimization, it's more like a single-side DMRG. Well, the matrix states are very elegant and are very powerful. So you can, as I told you, completely reformulate and rewrite DMRG in terms of matrix states and write an algorithm to optimize these matrices directly. It turns out, you know, if you ask me, DMRG is easier to implement, but the modern take on this is most people learn in terms of matrix state, and they do it with matrix states. However, you know, a matrix state code, like, you know, I give you a DMRG code, but a matrix states code would be probably twice as long in number of lines and harder to read. Okay, so I think that DMRG gives you more physical intuition in terms of, you know, how you write the Hamiltonian. Well, I mean, you can still do the same with matrix states, but it's just a little more cumbersome, if you ask me. Now, the thing about matrix states is that you can directly get a lot of information out of these matrices. And on top of that, you can engineer matrix states by hand. You know, you can actually take matrices with given symmetries and design a matrix state that's going to be a symmetry-protected topological state, or that's going to be a chiral spin liquid, or so and so on and so forth. You don't have the parent Hamiltonian for that state. You can cook it up. You can still cook up a parent Hamiltonian for a matrix state. But in principle, you can just, you know, propose arbitrary wave functions with any given properties, but by hand, by just basically specifying these matrices. And these matrices can be very small. You know, the bond dimension, the alpha, can be 2, 3, 4. And this is the case in the KLT state. For instance, the Affleck, Kennedy, Lieb, Tesaki state for the ground state of the spin 1 chain with biquadratic interactions. So this is a prototypical example of a state that can be written exactly in terms of a matrix states. The idea, of course, Affleck and company, when they wrote the ground state, they didn't write it in terms of matrix states. They wrote it in terms of projectors. They said, let's imagine that each spin 1 is split into 2 spins 1/2. Right? So the projection up is going to be up, up. Projection down is going to be down, down. And the zero projection is going to be up, down plus down, up. But with spins 1/2, you get an extra state, which is the singlet. And you have to project it out. You have to throw it away. So how do you do that? How do you create the ground state? Well, basically what you do is you put 2 spins 1/2 on each side, as shown here. You entangle one of them with another one of them on the neighboring side, forming a singlet like this. So imagine you put a product of singlets like this between spins 1/2. And there's no interaction between the spins 1/2 on each side. These are just singlet, 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 singlet. It's a dimer. But now you apply a projector between these two. And this projector basically is telling you that there is some degrees of freedom that are not favored and are thrown away. And that's basically the triplet state. And that implicitly is telling you that it is basically coupling these two into spin 1 effective object. Well, this can be done explicitly in terms of just 2 by 2 matrices. So this is just a matrix state with bond dimension 2. So it's actually really simple and elegant. So when you do matrix parallel states, what you're doing, you don't think in terms of you still have to do contractions and singular value decompositions and so on and so forth. Basically, what you're doing is but what you're basically doing is a variational minimization. You're minimizing the energy, the variational energy of that matrix parallel state, like this. In a way, that's the same as DMRG. So DMRG is doing optimizing your matrix parallel state, and whether you use a DMRG algorithm or an MPS-based algorithm, you'll get exactly the same result. Except
that's what happens when you are doing the sweeping, right? Before you start the sweeping, it's just a constructive. There's no variation.
Right.
So when do you start to do the variational part for DMRG?
All right. So yes, two things. So one thing is that with DMRG, I told you that you add one side at a time beforehand. So you don't you have to start constructing your chain from scratch, from zero. 2 sides, 4 sides, 6, 8 sides, and so on, until you reach the system size that you want. And then that's when you have your ansatz for your matrix parallel state that you want to improve. And when you start doing the sweeping, basically what you're doing is you're doing the variational optimization. In matrix parallel states, you put matrices by hand. So you have L sides, you put L matrices. L matrices times the number of degrees of freedom that you have per side. Remember that it's a matrix, but each one has a physical index. So it's a list of matrices. And you need to optimize all these matrices. And you start with, say, random matrices. And at every step, you minimize this variational energy, and you improve them. And the way you do this is doing singular value compositions and so on and so forth. So you still need to do a compression. But the fact that you're doing a variational optimization is more obvious in this case. One thing that I didn't mention is that another elegant thing about matrix parallel states is that they allow you to formulate a matrix parallel state in the thermodynamic limit when you have translational invariance. So imagine that you have translational invariance. Imagine you have a state like this, but it's infinite, right? So if it's infinite, this product will go forever to the forever to the right and forever to the left, right? But translational invariance also tells you that there's only one matrix, because all the matrices should be the same. There's no preferred position along the chain, so you only have to optimize a single matrix. And this allows you to formulate an efficient optimization for translational invariant states in the thermodynamic limit. It's called IDMRG, and there's also ITBD that do pretty much something equivalent. IDMRG does a variational minimization. ITBD does a sort of projection, using time evolution in imaginary time. All right, so I'm going to wrap it up here for matrix parallel states and switch to time-dependent DMRG now. So I'm going to have to close this presentation. Any questions about this first part? Feel free to ask. So I haven't discussed any physics. Hopefully, if I have time, by the end of this presentation, I'll show you some physical examples and nice applications of TDMRG. So TDMRG has an interesting story. This is some literature, but basically this is on the modern, or what we'd call adaptive time-dependent DMRG. All right, but there is a seminal paper that, for some reason, I forgot to list here, by Marston and Casalia, where they first came up with the idea of using DMRG for time evolution. And what they did was very simple. They calculated the ground state, and then they evolved the ground state using Runge-Kutta. And I'm going to describe that in a sec. So, but they didn't adapt the basis as they evolve in time. They always use the same basis, the basis for the ground state. And you know that when you do time evolution, you're mixing excited states, not only the ground state. And that basis basically won't work if you do time evolution. Might give you a short time description, but not long times. So then Giuffre Vidal came up with his ITEBD, or infinite time evolving block decimation idea. Basically rewrote DMRG for infinite translational invariant states and did his projection. And then with Steve White, we realized that we could do it within a DMRG framework using the same language. But it turns out that, of course, these people were working on the problem at the same time, so we both published this paper simultaneously. Then we came up with ways to do it for systems that don't have a nice Suzuki trotter decomposition, like systems with in 2 dimensions or long-range interactions. Scholbeck and White wrote this review. Then there are my lecture notes from Vietri. And there are actually new developments that I haven't listed here, because you can actually do, with matrix pro states, you can do continuous matrix pro states in the continuum, and you can do time evolution in the continuum. You can actually use what's called the time-dependent variational method to evolve matrix pro states. That I won't cover here. Again, so I'm going to describe it in terms of DMRG. If I do it in terms of matrix pro state, I don't need to spend more than 2 slides. That's the nice thing. I have to apply unitaries every 2 slides, and that's it. But in DMRG, it's a little more explicit, if you will. So we do this block decimation, and we calculate the ground state, as I described. What we want to do is we want to solve the Schrodinger equation. So we calculate the ground state, or any state. Imagine we have an initial state. It could be any arbitrary state. All spins up. It could be a product state. It could be a random state. And how I generate that state doesn't matter. I just need to have a nice matrix product state that describes that state. I can use, for instance, another Hamiltonian to generate the ground state. And then time evolve with a physical Hamiltonian that I'm studying. So the idea is to evolve the ground state, but as I said earlier, the wave function at finite times is going to be a mixture of excited states and the ground state. It's going to be, and each of them is going to enter into this expression with coefficients that are going to vary with phases corresponding to their energies. And this could have very fast variation in time or very slow. And in order to resolve all these scales, it's going to be quite challenging. But DMRG can do it. So this is the original formulation by Casalini and Marston. They started, so this is time. I discretized time in small steps. And at every time step, what they did is they evolved the wave function using Runge-Kutta, or Runge-Kutta, if you're German. So the thing is that they use the Hilbert space that they optimize for the ground state. So these guys, Luo, Xiang, and Wang, realized that in reality that's not an optimal idea. If you want to go to long times, what you need to do is adapt your basis as you evolve in time. So what you have to do is target the initial state, you evolve to time tau, and you target now these 2 states, you evolve to time 2 tau, and you target these 3 states, so on and so forth. And you do that as you sweep. So Casalini and Marston didn't do any sweeping because they didn't have to optimize the basis. So these guys did the sweeping, and they targeted multiple states. And that's very good. It's a huge improvement, but it's highly inefficient because you have to keep track of all the history of the state. And it's not necessarily clear that the ground state is going to have anything to say up here in the basis for time for tau. So this is how we do it. By the way, in these two papers, they use Ranchikara. After ITBD, we realized we could use Suzuki Trotter. And you heard from Adrian the Maestro about Suzuki Trotter, so I'm going to skip most of the discussion. But basically, what we want to do is apply the evolution operator in small steps. So instead of using Ranchikara to solve the Schrodinger equation, let's say, explicitly as a differential equation, we apply the evolution operator in small time steps. And so imagine that this is your full Hilbert space, and your ground state, actually, our ground state, lives in a small sector here that is spanned by the matrix process states. So imagine that my matrix process states live in a small fraction of this Hilbert space, but those that are good for my ground state live here. Now what I'm going to do is, as I evolve in time, I'm going to adapt my basis. This is the same as changing the matrices in the matrix process state. I cannot use the same matrices. So the way we do it is by sweeping, right? So we do it by, first, we split the system into even and odd terms. So first, we have to assume that we have a local Hamiltonian. If we have a local Hamiltonian, the Hamiltonian only involves nearest neighbor terms. And we're going to split the Hamiltonian into even and odd partitions, the same as Adrian explained. And this is what's called the Suzuki Trotter decomposition of the evolution operator. So now our evolution operator can be written as a product of, let's say, local evolution operators or pair evolution operators acting on neighboring sites, red and blue bonds. And each of the blue bond commutes with the other blue bonds, and each of the red bonds commutes with the other red bonds. But the red and the blue don't commute, and that introduces the error in the decomposition. And this is what's called a second order decomposition, a first order decomposition. Actually, this is a second order decomposition. So this is what you do. This is a first order decomposition that has an error of the order of tau square. Just write the exponentials as the product of the two exponentials, but you can have higher, cook up higher order expansions. There's a recipe for that. I won't go through it because it's mathematical and technical, and it's not worth it right now, but you can look at it. So for first order, you get this, the product of the two exponentials. Second order, you get actually something like this. Actually, this is the final result. So you apply it to the, say, red bonds with the Hamiltonian over 2, the blue bonds with the Hamiltonian, and the red bonds again with the Hamiltonian over 2. So you need to do act 3 times on every, more than once on every bond. And you can do fourth order, and fourth order becomes a mess. Basically, you have the closest form has 7 products. But what's the advantage of using fourth order? Well, maybe you can use a larger time step, but you need to do more exponentials. So maybe you want to use third order with a smaller time step. It's just so we use basically we don't use this formula. We use second order with a small time step, and we control the error by changing the time step. I'm going to skip this. This is how you calculate the exponential for 2 spins, for instance. Actually, I'm just telling you this for the sake of completeness. But if you do Python, there is a function that exponentiates any matrix for you. So the way you do this, you calculate the matrix that you want to exponentiate. This is your 2-side Hamiltonian. And if you want to exponentiate it, you know that there's a series expression for calculating the exponential of a matrix, but you don't need to do that. You rotate it to the eigenbasis, you calculate the eigenvalues, you exponentiate the eigenvalues, and you rotate it back to the original basis. So how do you evolve the wave function with DMRG is as follows. So again, we only need to apply the evolution operator every 2 sites at a time. And DMRG always has these 2 sites in the middle that are in the spin basis. So what we're going to do is apply the evolution operator to these 2 sites. It's basically a 4x4 matrix or operator that acts like this. And it gives you a new wave function. It doesn't change the left block. It doesn't change the right block. It only changes the coefficients here. So, and the way we do it in the algorithm is as follows. So imagine this is your DMRG. So we actually finish the DMRG here at the end. And this is when we want to start doing our time evolution. And the way we do it is we first apply the evolution operator here. Now, remember that we do it every other bond, because we are doing only the evolution on the red bonds, let's say, not the blue bonds. So we leave that, the one in the middle as it is. We just grow the block the same way we do DMRG, but we don't need to do Langshos, or we don't need to calculate the ground state or diagonalize the system. All we have to do is apply this little evolution operator on these 2 sides. And it's a super fast calculation, right? Because it's a 4x4 matrix acting on 2 spins. You don't do evolution on this. You do evolution on this. You don't do it on this. So you do it every other bond until you reach the end. And then you do it to the right. But then when you do it to the right, you do it only on the blue bonds instead of the red bonds. And you do as many sweeps as you need, depending on the Suzuki-Trotter breakup that you're using. So if you're using second-order Suzuki-Trotter decomposition, you need to do blue bonds over 2, right bonds, blue bonds over 2. And that's 1 time step, right? So what happens? Any questions so far? How are we doing? So again, this is just the same algorithm as DMRG. You don't change anything in the code, but in the part when you were calling the Langshos diagonalization. So instead of doing Langshos diagonalization, you figure out whether you're on a red or blue bond, and you apply the evolution operator. And the rest stays the same. So it's very easy to implement if you have a working DMRG code. We actually wrote the code, did the calculations, and wrote the paper in 1 week with Steve. Once you have the idea, it's so easy to do. So the Suzuki-Trotter decomposition can be applied only for local Hamiltonians, called nice Hamiltonians. But if the Hamiltonian is not nice, you can do the time evolution in various ways. You can do what we do is what we call time step targeting. So we take our wave function, we evolve it using any method you want. You can use Runge-Kutta, or you can use a Krylov decomposition of the evolution operator. You can take your Langshos matrix of H, exponentiate it, and apply it to your state. That's what Krylov means. And that's nice because it has, it's a higher order, if you will, approach than Runge-Kutta. Runge-Kutta is 4th order. So, but when you evolve in time, remember that I told you Casaletti and Marston didn't target states properly. Wang, Luo, and Xiang targeted everything along the time evolution. What we're going to do is we're going to just target 4 intermediate states in between time 0 and tau. So we're going to take 2 smaller time steps, take these 2 steps, 2 states, do sweeping, and optimize the basis, and then at the end do Krylov or Ranchikara and get the new state at time tau. And we repeat it again, but we only need to keep track of these 4 states. We don't need to keep track of all the entire history of the state before that. And we keep repeating and so on and so forth. So these 3 states can be obtained easily from the Ranchikara states. You remember that Ranchikara is written like this. Your function at time t plus tau is your function of t plus 1/6. It's like a weight average of 4 states, k1, k2, k3, k4. And these states k1, k2, k3, k4 are obtained as your function at time, say, t plus k1 over 2, and so on and so forth. So it turns out that you can write these other 2. So what I'm doing is I'm writing this state. But I can write these 2 intermediate states also, in terms of those k1, k2, k3, k4. So all I have to do is calculate this k1, k2, k3, k4, target this k1, k2, k3, k4 through the time interval. Actually, I need to target these 2 states. And then at the end, do the time evolution after a couple of sweeps. So here's where the idea of multi-state targeting enters. Remember that I told you that it's important to use all these states in the reduced density matrix. And we weight these states in the reduced density matrix with different weights. And we came up with the weights empirically. You know, it's 1/2 of this state plus 1/4 of this plus 1/4 of this, something like that. So what are the sources of error? If you do Suzuki-Trotter, you have the time step error and the DMRG error. So if you assume that your DMRG error is under control, you just keep a large number of states, the error comes from your expansion. And from the, if you do Krylov or Ranchikara, it turns out that the error is dominated by the truncation error. And that's because you have to keep track of all these intermediate states, and that gives you, tells you that you need to use a larger density matrix and use more DMRG states. So one recipe to get rid of the truncation error is to fix it at some small value. Let's say I fix the truncation error to 10 to the minus 8. So DMRG automatically figures out how many states you need to keep when you diagonalize the reduced density matrix to keep the truncation error below 10 to the minus 7, 10 to the minus 8. And if you do that, you'll find that the number of states that you need to keep grows in time, typically. So at some point, your simulation will blow up. But while it works, the entire evolution is going to be dominated by just what kind of decomposition you use for the evolution operator. And this is something that I show here. So we took the error between some observable and the exact observable, and for different approach. If you look at Suzuki-Trotter, if you increase the number of states, all the errors saturate. And they saturate because you cannot reduce it any further by keeping more states, because the error is dominated by the Suzuki-Trotter decomposition. If you do Ranchikara, you see that the error still goes down as you increase the number of states. So that tells you that rather than worrying about the Ranchikara error, you have to worry about how many states you keep. And the error, of course, scales as expected. Right? You see here that the error scales as the corresponding power, depending on what Suzuki-Trotter decomposition you use, while in Ranchikara, the error depends, well, it's dominated by the truncation error. Again, I told you that earlier that if you keep the truncation error constant, as you evolve in time, you're going to have to keep more and more states. And this is a typical example. This is what happens after you perturb a Haldane chain with 32 sites, and you measure some, you evolve it in time. And this is, you see that it grows very fast. I mean, this is a small chain. You have to keep 1,600 states to get it to time the order of 8 in units of J. Why it grows like this? So that's another problem that we need to figure out. So let me, okay. If, again, Suzuki-Trotter works very well for one-dimensional systems with local interactions, but again, you need to use Ron-Shakara to evolve in time if you have long-range interactions or in 2 dimensions. And you have to be careful also, if you do time evolution with Ron-Shakara, Ron-Shakara is not unitary. It's not unitary evolution. So you may, you have to keep track of your energy to make sure that your energy is being conserved, right? And and you do that by just keeping more and more states. Another thing that you can do is using Krylov, which is unitary. So applications. Well, here in the next 20 minutes or so, I'm going to walk you through a number of applications. I told you, by the way, this can all be done also with matrix cross states. It can be done with matrix cross states. There are tricks to do long-range interactions. I didn't discuss that, but there are some papers by Steve White and Miles Tudemeyer, and also by Frank Polman, where they show how to do it with unitaries and applying swap gates. So the nice thing about time-dependent DMRG is that now all of a sudden a new zoo of problems is within reach, and we can study transport in nanostructures, and not only in equilibrium. We can study transport away from equilibrium by applying large biases. We can apply time-dependent perturbations, pumps, and look at spectral properties, the optical conductivity, for instance, spectral functions. Remember that the spectral function is nothing else but the Fourier transform of the single particle Green's function in real time. Or you can do it in imaginary time too. You can look at quenches, time-dependent Hamiltonians, decoherence, and so on. Floquet, physics, etc., etc. This is an example of spin transport. Imagine that I have a half polarized chain. I take a spin chain, I polarize half of it up, half of it down, and I can do that in DMRG. I mean, this is a trivial matrix plus state. You can write it down by hand if you do matrix plus states, or in DMRG you can apply a magnetic field in this direction to half of the spins, in this direction to the other half of the spins, do DMRG, ground state DMRG. That will give you the initial state. And then you time evolve with the actual Heisenberg Hamiltonian. And this is the projection of the spin as you evolve in time. And you see that basically you have a domain wall that is melting. And if you plot this domain wall in the time and position axis, you see nicely the light cone. And you can measure the spin velocity by just looking at the slope of this curve. This is for different cases. It turns out that by tuning, if you take an XXZ chain, by tuning the value of delta, you can go from diffusive behavior to ballistic behavior here. Actually, I think the delta is the other way around. So this is ballistic. This is for the isotropic chain. This is for the anisotropic chain. It's the other way around. OK. The question is, I told you earlier that the number of states that you need to keep as you evolve in time grows. And this is, it cannot be, I mean, the only reason for this behavior can only be that the entanglement is also growing. And why it grows and how does it grow can be sort of predicted beforehand in some particular cases. You have different scenarios. You can do a global quench, where you basically change globally a parameter in the Hamiltonian. You can do a global quench, where you apply a local perturbation in one site or a few sites. You can do a periodic quench. You can do like a Floquet, do something like that, periodic perturbation, or an adiabatic quench. Adiabatic quench is basically you ramp up some parameter in the Hamiltonian adiabatically, and you're always close to the ground state. And in that case, the entanglement in principle won't grow if you go slowly enough. Because in the ground state, you always have an area law. But again, all of a sudden, we're no longer in the ground state. We're in some mixture of highly excited states, and it's not trivial to, beforehand what the behavior is going to be. But in a global quench, for instance, you can have a behavior like this. This is I think, a transverse field IC model. I don't even remember what this is. This is from this paper. They look at this problem. Basically, how does the entanglement grow in time and why? And how does it depend on the kind of perturbation that you apply? This, I assume this is a gap system with a finite correlation length. So at some point, your entanglement will stop growing. But in the meantime, you see that the entanglement entropy grows linearly. And the behavior can be explained as follows. Imagine you take a region in the center, and you look at the entanglement between the center and the rest. And what you can assume is that basically you're creating quasi-particle pairs inside this region. One of the quasi-particles is going to blow away from this region into the environment, while the other one is going to remain within this region. And those pairs are going to be responsible for the entanglement between the inside and the outside, and how the entanglement grows. Because beforehand, you just have the ground state area law. But now, all of a sudden, as the number of quasi-particle pairs proliferates, it becomes a volume law, right? And in the global quench, so if you have a local quench, this happens only, say, at the boundary. You only have one pair that propagates. But if you have a global quench, you have an extensive number of pairs. And that tells you that global quenches are bad, because global quenches give you a volume law. So long story short, a global quench will give you behavior of the entropy that grows in time as an exponential. A local quench will eventually give you something that grows linearly with time. And an adiabatic quench, as I told you, you always remain close to the ground state, so you don't have to worry too much. So again, all boils down to what kind of perturbation you're going to apply. And you can, in advance, estimate the computational cost of your simulation. That's why we all prefer local quenches, right?
Can you give some physical picture on the local quench behavior, log T behavior?
The log T?
Right.
Where was it? Here. Or the idea is that imagine you create, you're looking at the entanglement of the left side with the right side. And you create a local perturbation here, right? And you're going to create a quasi-particle pair, let's say. And one's going to blow, flight to the left, and the other one is going to fly to the right. So this is going to give you entanglement between this region here and this region here. And we know that in a chain, the entanglement grows as a log of the length of this region. And the length of this region is the velocity times the time of the quasi-particle. So the velocity of the quasi-particle times the time. So that tells you that the entanglement is going to grow as the log of v times t.
I'm confused. If there's only one pair of quasi-particles, I expect it's log 2.
Right. But yeah, you assume that this, you're right. This pair is actually getting scrambled with all the particles here. This is a very qualitative, hand-waving picture. But everything here, inside here, is getting scrambled, and it's going to get entangled to everything that this spin left behind when it flew here. So it's like, let's put it this way. If you look at this light cone, right, you see that you're basically messing up with all these spins here and all these spins here. So now your entanglement is going to be proportional to the length, well, the log of the length of this segment here. That's what's happening.
So it seems the quasi-particle picture is good to explain the global count. For local count.
Yeah, yeah. Mm-hmm. All right, so again, another example. For instance, we can study transport, as I mentioned. So this is all about, everything I have to say about DMRG. Well, actually, I have more to say. So maybe I should go quickly over examples, because I want to tell you how you do finite temperature DMRG also. So if you want to study transport out of equilibrium, for instance, imagine you have 2 leads connected through a weak link, and you apply a bias between the left and right leads or halves, and you look at basically the time evolution of the current through the link. And this is what it will look like. You have a transient, and eventually you reach a sort of plateau or quasi-steady state. And it's not quite a steady state because your system in the end is finite. So this chain is going to be finite. It's going to have like 50 sites or 100 sites. This one too. So when you reach the end of the chain, the current is going to get reversed because your electrons are going to bounce back and be reflected. And they're going to come back and give you an inversion of the current, as shown here. And you can overcome that by taking longer chains or by taking what's called Wilson leads or damped boundary conditions. But I'm not going to get too technical. The long story short, if you average over this plateau, imagine you have different biases, you average in this region, you can calculate the entire IV curve like this. And in this case, we are comparing to Bethe-Ansatz prediction for spinless fermions. And you see that the agreement is very good, except for large biases. And the reason why you don't get agreement for large biases is because of the curvature of the dispersion. For large biases, the dispersion is no longer linear. You start seeing the lattice. And this is basically an effect of the lattice. The Bethe-Ansatz assumes that you have linear dispersion. And here, this is for a resonant level or double barrier. You can do the same. You can study quantum dots, basically Kondo impurities, and do the same. Calculate the entire, you look at quantum impurity as you can look at as a function of the conductance as a function of magnetic field, for instance, for different bias, gate voltages, and so on. This is what I refer to as Wilson leads. Basically, what you're doing is you're changing the hopping as you move away from the impurity. This is a trick that we use to improve convergence and get rid of finite size effects. But skip this. Another comparison with Bethe-Ansatz. This is away from equilibrium, and you see that here we're comparing with functional RG and fourth order perturbation theory, and you see that FRG works actually quite well. Here, an interesting effect for large biases in Kondo is that you get a negative conductance, and this is due to the Coulomb blockade peaks in the density of states. This is how the steady state depends on the initial boundary conditions. If you do transport, you can do it in different ways. You can apply a bias at time 0. You can start with 2 leads at different biases and connect them at time 0 to the impurity. Or you can start from a non-interacting impurity and turn on interactions at time 0. And these are the 3 scenarios. The red one, as you see, the blue one corresponds to quenching the interaction. You know, this looks like non-interacting fermions. You turn on the interaction, and poof, it goes to the steady state for the interacting case. Two important applications. In the next 5 minutes or 10, I'm going to go through these two examples. One is that you can use DMRG to calculate spectral properties, and it's a very efficient method to do it because it's a local quench. So if you calculate spectral function, what you're doing is basically calculating the Fourier transform of the real-time single particle Green's function. And this corresponds to applying an operator at time 0, evolving the state in time, and applying another operator at time t. And we can do that efficiently with DMRG. For instance, you can do spin-spin correlations like this. You apply S plus at time 0, S minus at time t, and this gives you the correlation between two sides at different times. And this is what it looks like if you do this at the center of the spin chain. This is the quantity that I'm plotting, and it looks like this. And this basically gives you this quantity in real space and real time. Now what you have to do if you want the spectrum is you want to Fourier transform it. So first you transform it in time to frequency. But first you transform it to momentum. And this is the fishy part, right? Because we have open boundary conditions. How do we do momentum? Well, you can always define momentum with an open for an open chain as well. It's like a particle in the box kind of momentum. But another way to do it is to assume that you have periodic boundary conditions and stop the simulation before you hit the boundary. And you see that you get a very nice cosine wave, and you Fourier transform this cosine wave, and you get a nice sharp sort of quasi-delta peak, right? So this actually is a Gaussian or Lorentzian, depending on how you Fourier transform, what kind of window you use, and what kind of window function. And you see that there are some artifacts. You see some wiggles here. You can get rid of those wiggles with a different windowing scheme or by going to longer times. And if you plot this now as a function of momentum and frequency, you get the entire spectrum like this. This is for spin 1/2 chain. This is for spin 1 chain. And you can do it for fermions, like this is a TJ chain, and you see the entire spectrum with the Hall-on branches, the spin-on branches, and everything else. You can calculate optical conductivities, et cetera, et cetera. And so that's for spectral functions. For finite temperature, you have to introduce some really nice fun tricks. And this is how it goes. So now I'm going to focus on finite temperature. And I hope you're going to enjoy this part because it's a lot of fun. I have 5 minutes, I know. So I'm going to rush a little bit. So imagine we want to represent an operator like this. This is, before we were talking about wave functions. And I wrote the wave function as a matrix. Now imagine we have a matrix like this. And this matrix is encoded by these coefficients, A, J, K. I can imagine that I have a state now, which is a quantum state. It's a vector that has the same coefficients, J, K. So this is what's called Liouville representation. Now I'm writing a matrix or an operator as a vector in Liouville space. And you see that I use this two-bracket notation. And this is just representing this projector here. But these two are equivalent because the coefficients are the same. If I take, for instance, my operator to be the density matrix, we know that the time evolution of the density matrix is given like this, by this expression. If I do it explicitly, I can write it as, for each matrix coefficient jk, I can write it as a product between this, what's called super operator, which is called the Liouvillean, on the density matrix. Now I'm going to write it in the Liouville representation, and it's basically boils down to this. This is like a Schrodinger equation for the density matrix, where instead of the Hamiltonian, I have the Liouvillean. Now I'm going to do another trick. I'm going to use, instead of Liouville representation, what's called thermofield representation. Thermofield representation was an offspring of Takahashi and Umezawa, particularly Umezawa. They have this review on this. This is a technique that's well known in high energy physics, but not as popular in condensed matter. So basically what we're going to do is we're going to square our Hilbert space. You know, imagine we have a chain. I'm going to create another chain identical to my physical chain. And now I'm going to have two Hilbert space, the Hilbert space of my physical chain and the Hilbert space of my copy. And this is called the thermofield double. So for each state x on this Hilbert space, I'm going to have an identical twin x tilde living on this Hilbert space. But now I can write any function living on this double Hilbert space as this. J lives on the physical space. K tilde lives on the thermofield copy. And now I need a coefficient AJK, right? So it's going to have two subindices. That means that I can use these coefficients to encode an operator, right? The original operator A, I can write it now in the thermofield representation as a pure quantum state. And these coefficients contain all the information about my original operator, so I can just time evolve it. I can do whatever I want using time-dependent DMRG, because this is a pure state, I can evolve it. So how do we evolve it? We evolve it using the Liouvillean. And the Liouvillean, it turns out that is nothing else but H minus H tilde, where H tilde is the Hermitian conjugate of H. If the Hamiltonian is Hermitian, it's just the same. But acting on the thermofield doubles. And you can use DMRG to do time evolution of operators instead of states. So now imagine that we want to do a time evolution in imaginary time of my density matrix. Well, I'm going to run out of time. Unfortunately, you're probably hungry, as I am. So at 12 o'clock, I started like getting. Anyway, so it turns out that you can write any thermal observable like this as a quantum mechanical average in this formulation. So you can work with pure states, take your observable, sandwich your observable with pure states, and you're going to get the thermal expectation value. If you use the density matrix here as but you have to be careful now of what state you're using, here to sandwich your operator. So what state do we use? We actually use the following state. We start from the maximally entangled state at infinite time, and we evolve it with the exponential of the Hamiltonian over 2 times beta. Beta is 1 over the temperature. The justification is all here. You can look it up. It's very simple and elegant. So long story short, it comes to this. It all comes to this. You start at infinite time from the maximally mixed state. You can write the maximally entangled state. The maximal entangled state is the maximal entangled state between your physical spins and your ancillas, or your thermofield doubles. And you can cook up a Hamiltonian that is going to give you that state. Or you can write it as a matrix plus state. Because it's basically, for spins, it's just a product of singlets or triplets on all these pairs. It turns out, will give you the identity matrix. And the identity matrix is basically the density matrix at infinite temperature. So basically what you're doing here is you're starting from beta equals to 0 or from infinite temperature. And you're evolving the density matrix in imaginary time. And the way you evolve it is by applying this evolution operator, which is, as I told you, the exponential of h. Where's beta here? Oh, beta is missing. H beta over 2. And this is what people in quantum information actually call purification, and they've known this for a long time. Actually, Frank Verstraete has a paper that came up maybe before ours, where he talked about purification with matrix-exposed states, and we did it with DMRG, but with DMRG we used this thermophile idea instead. And so it's just, it's several fields coming together, quantum information, high energy, and condensed matter, into a nice new idea. So unfortunately, I'm out of time. Here I show you basically how a singlet or a triplet represents a density matrix at infinite temperature, right? If I take, imagine I take a singlet, I trace over the ancilla or the thermophile double to calculate the reduced density matrix of the physical spin. I get the density matrix for a single spin at infinite temperature. And if you have many spins, what you do is basically you do a product of singlets, as I told you. Now with this, you can calculate thermodynamics. You can do evolution in imaginary time and look at specific heat, magnetic susceptibility. You can add frustration and do it for the J1, J2 chain. You can do it for Kondo. Here you see the finite size effects. Because as you go to low temperatures, you have a gap, a finite size gap, and you get these artifacts. Well, I think, and you can calculate spectral functions. You can combine evolution in real time and imaginary time to calculate spectral functions or transport at finite temperatures. This is an example, and this is the end. Right on time. OK, thank you very much. Sorry for rushing, but there was a lot of material that I wanted to discuss. We have time for questions. Oh, right? 5 minutes.
Maybe I'll start with one. So you emphasized several times that DMRG works much better when you have open boundary conditions, but not for periodic boundary conditions.
Right.
Well, the obvious difference is that for periodic boundary condition, you actually have a ring. So when you cut it, you actually have two boundaries.
Right, correct.
So you double the entanglement, you have to square the number of states.
Right.
Is that all that is, or you have additional reasons why it doesn't work as well?
Right. The structure of the matrix-exposed state is the additional reason, the second reason. Remember, let me go back. Oh, it was in the other presentation, sorry. Instead of starting the slideshow, I'm going to just go. It was here. Was it here? So you see the matrix-exposed state for periodic boundary conditions has a matrix at the origin, right, and a matrix at the end.
Right.
While DMRG actually is using a different wave function, which has a vector at both ends. So that prevents you from properly describing the entanglement between the first and the last side.
Well, it's just because it's not recognizing that the endpoints are actually also boundary points.
Right, right.
So if you also treat them as boundaries, can you actually remove that deficiency?
You cannot do it with the DMRG sweeping algorithm, with conventional DMRG.
Obviously, this breaks the translation symmetry, right? Because the endpoints are not really
correct. So you're putting by hand a variational wave function that breaks translational symmetry to describe a system that has periodic boundary conditions. Right. So Frank Verstraete and Sirac were the first to realize this, and they proposed an algorithm for periodic boundary conditions. But this algorithm is very unstable because of the normalization of the wave function. I told you that normalization is very important. And when you have left and right normalized states, that's very easy to do. But here, you don't have left and right. You know, it's periodic. So the normalization is extremely delicate. And It turns out that it's really hard to implement, and no one is really using it, to the best of my knowledge, at least.
More questions? Okay.
Yes.
Everybody. Oh.
So is there an easy way to modify your yesterday code to do TDMRG?
You mean the Python code?
Yeah, yeah, yeah.
Yes, you need to introduce the wave function transformation that I described. That's something that you need for TDMRG, and I'm going to do it for you. So I have the code in C++. I'm just porting it to Python. So it will take me a couple of days, but I will post it there. So check next week.
Okay,
it'll
thank
be
you.
there. Where is it? Yes. So here, I told you about this wave function transformation. This is a very important step that you need to introduce before doing time evolution. And that's what's missing in the code that I gave you. So I'm going to do that, and at the time evolution, it's just straightforward.
Thank you.
So I'm wondering, so if your Hamiltonian has some other extra conserved quantity, then will TDMRG also conserve that automatically, or that will also suffer some like conservedness from the non-unitary evolution that it's using?
Right. So good point. So if your Hamiltonian conserves some quantities, then you just use quantum numbers, and you worked in the Hilbert space you are interested in. If your Hamiltonian is like if you're using some Hamiltonian that doesn't conserve particle number, for instance, or total spin, you can you have to relax the. I mean, you can still store the operators in blocks, but you cannot store the Hamiltonian in blocks. So you have to be careful about how you implement it. The example I gave you doesn't have quantum numbers, and basically you're working in the grand canonical. So you can add a magnetic field, and automatically it will give you the magnetization curve. If you implement quantum numbers, what you can do is just fix the magnetization instead, and then do a Maxwell transform and go from field to from total spin to field and get the magnetization curve. It's more convenient to work in when you have good quantum numbers and good conserved quantities. It's better to work with quantum numbers, and because the calculations are more efficient and faster. But there are some cases where, I mean, Shibata and collaborators propose working in the grand canonical with what they call damped boundary conditions. They say it's easier to reach the thermodynamic limit. There are different points of view, but in general, you want to, if you have good conserved quantities, you want to work with those quantities to optimize your calculations and make them more efficient. If you don't have conserved quantities, you just relax the quantum numbers, and the time evolution will work as usual. I mean, you won't lose unitarity unless you're imposing a symmetry artificially that is not there, right? So you cannot just fix the quantum numbers and time evolve with Hamiltonian that doesn't conserve the quantum numbers. That's something that you should not do. What else? Yeah, well, I don't know if that answers your question.
More questions? Okay. that people are more hungry for knowledge than just food.
How to impose non-abelian symmetry in tensor network?
That's I invite you to do it. I've never done it. It's people have implemented SU2 symmetry. You have to keep track, do a lot of bookkeeping and keep track of all the Clebsch-Gordon coefficients. I'm not sure it's worth it unless you are doing like a super duper state-of-the-art calculation, like I mentioned Steve White's and Scholweg and Davenbrock calculation for the Kagome lattice. They use SU2. There are some people that use SU2 for Kondo impurity problems and numerical normalization group. In my opinion, I don't know. It's for the kind of calculations that I do, it's not worth the effort. But if you're planning to do something really, difficult that needs thousands of, for these Kagome lattice simulations, they use 30,000 states or something like that. With SU2, it's just a brutal calculation. They use the entire cluster for 6 months. I don't punish my students like that. So, sorry, Uli. It's just technicality. I don't know if you use actually matrix express states. I don't know how easier or more difficult it becomes, to be honest.
So maybe I should mention one of the people who actually implemented it, Xiushu Gong, was actually a postdoc here until
that's
4 months ago. So it can be done, and it can be done here, actually.
Right.
Any more questions? Well, if not, let's thank